Hey, so hello everyone. So my name is Wei Zhang, and I'm from Hermes International Lab. So today my topic is distributed Affix-Based method search in self-describing data files. Um, so nowadays the scientific uh, scientific data is really huge, and also in terms of the volume and also the variety, and most importantly, it is ever growing in terms of its velocity. And also a common practice for enhancing the findability and reusability of scientific data is to attach auxiliary attributes on the data. And all these, most of the auxiliary attributes are actually in the form of key value format. So, and usually scientists need to locate the data of interest by sifting through of these metadata attributes. So here are the two key observations that we have observed from these scientific applications. The first one is actually no pair needs to be accurate. So here's an example. So take a look at this SPSS data set where scientists possibly just want to find nebulas that are round shaped. So it doesn't matter really if it's like in between round or maybe completely round or maybe have some like rounded boundaries, whatever. But usually when scientists trying to do their study against the data set, they just want to simply search for, okay, maybe a nebula image that is of round shape. And another use case is that in the LSM data sets, the scientists are collecting the brain tissue images through the lattice light sheet microscopy. And so they might just want to record like the date for collection and also date for transformation of the data. So when they are searching for the data, they probably don't exactly know like what they are trying to search for. For example, if it is the collection date or if it's like transformation date. But overall, they just mention, okay, I just want to search for a particular set of data that potentially processed or maybe never collected through a particular time period. So in this case, both the key part and value part of the query are affixed. And also, more importantly, no one can actually remember every attribute in its exact form, especially with the explosion of the metadata attributes in some of the data sets. You can imagine that it's really, really tough for people to remember everything. So that's why we need this Affix-Based metadata search capability to ensure that we scientists can issue fuzzy metadata queries. And so now let's take a look at the meta search and HDL5. So the metadata in HDL5 is actually organized in a hierarchical structure, and still the attributes are still in key value format. And most of the scientific applications today are parallel or distributed applications, and they might want to access multiple different HTML5 files or some other type of scientific data formats. And also, these files are distributed on parallel file systems, and to achieve the refined I/O performance, usually they tend to employ a parallel data management system to handle the access against these different files. So in this case, the question is, can we provide Affix-Based fuzzy search capability of both key and value of any attribute efficiently? So for this question, we're trying to see like to provide efficient Affix-oriented meta search. What do we aim for actually? So essentially, there are two different goals we need to achieve. The first one is to support Affix-oriented method search, which actually allows you to contain the affixes on the part and also on the value part in the query condition. And secondly, you need to support two different query scenarios because not all the applications are having the support of MPI, and MPI support may not be always available depending on which environment you are running your application. So in this case, you should consider for the applications without MPI support, it's gonna be all the queries are sending independently, and also for the applications that are running on HPC with MPI available, you can send your query collectively. Also, there are two additional goals that need to be satisfied. First is the minimized communication cost, and then secondly, the adaptability to the server count changes, because your application can start with a particular setting and then later on maybe reboot it with a different setting that with different number of servers. So because every metadata attribute starts with its key, and to address the affix-based keyword search, we need to look at how do we possibly first satisfy the affix-based search against the key. So here this is the question about affix-based keyword search in a distributed setting. So there are three different methods for building the index for the keywords around in a distributed environment. So one is called the document partition approach, where you basically build index locally, and the index partition is following the partition of the object or files. So with this approach, there are already some existing work like Target or Somata, which are actually building the local index on each partition. And also with this, other queries need to be sent through all the partitions to retrieve the complete results. And then there's the term partition approach, where you basically distribute the metadata index based on the metadata attribute itself. So in this case, we can do full string hashing, which is to do the hashing against the entire key. So with this, it is common to see that we distribute different keywords in Dynamo or Cassandra or HBase, where we basically calculate the hash against the entire string. And also there's the initial hashing, which the idea is to hash the metadata attributes by the initial characters. So prefix hash tree has been proposed to achieve this type of functionality. However, the thing is, with document partition approach and full string hashing approach, you cannot avoid query broadcasting when performing affix-based queries, like for example, prefix, suffix, or infix. You need to go through all partitions because you are not really certain, which affix is actually can be satisfied on which partition, right? So it's not deterministic. And then for initial hashing, there's an issue with uneven index distribution, and that actually causes uneven query workload. So here, when considering the distributed affix-based keyword search, here are some of the requirements. So functionality-wise, we need to support prefix search, suffix search, infix search, and exact search. And also for efficiency consideration, we need to avoid document partition approach and full string hashing because we don't want to have any query broadcasting. And then for load balance, we need to address the imbalanced keyword distribution and also the skewness of keyword popularity, because some of the keys might be more popularly searched over against other attributes. And then for scalability, we need to make sure that at any scale, we can still satisfy the functionality, efficiency, and load balance requirements. So with this goal, we devised DART, which is called the Distributed Adaptive Registry. And that one is actually partitioning the entire search space into a series of virtual nodes following a tree-based approach. And then with the, let's say, the number of physical machines that you have, and with the tree depth that you can possibly find or customize, it is actually essentially very easy to calculate what is a appropriate depth of the tree. And also, we divide this partition tree into different root region and sub-regions so that the query can get routed to different regions and virtual nodes. So when building the index around this distributed adaptive registry, the basic goal is to balance the keyword distribution. So it is sort of we're considering the randomness. So randomness leads to the balanced keyword distribution. However, it leads to current broadcasting. And also we need to also we consider another aspect is the determinism that brings the efficient key lookup. However, the thing is with this thing you can have imbalanced keyword distribution. So here we're striking a balance by selecting the eventual virtual node between the calculated base virtual node and alternative virtual node. So these, the calculation of these two virtual nodes are actually very simple and can be finished very efficiently. So here, based on which one has the lesser number of index keywords, the eventual virtual node will be selected. And then after that, we need to make sure that we deal with the skewness of the keyword popularity, right? So in this case, we also choose a set of replica nodes that are selected based on the predefined replication factor. And then so our algorithm makes sure that the distance between every two selected replica nodes is roughly the same, so that we can further ensure an even replica distribution. And last year, we devised DDMs to support the affix-oriented meta search on both keys and values. So with this, we achieve, so on the API level, we provide support for affix query on both keys and values, and also we have this load distributor which actually encapsulates the Dart partitioner, and also we have this routing algorithm coming from Dart, and also they provide this response processor to do some pre-processing against the meta search result. And also on the server side, we designed a compound index structure that can process affix-based query on both keys and values very efficiently. And also we provide this index persistence mechanism so that we can save the metadata index onto this and be able to recover index when the data set or let's say the application are migrated to different sites or maybe starting with a different configuration. So with this, we are actually seeing a significant query routing, and we can reduce the communication overhead, and we can have more simultaneous query in the same time window. And also you can consider that we're actually just distribute all of these metadata attributes indexes around this Dart plate, I would say, and it's very interesting. And for the adaptability device, because we can define a maximum server count, so that later on you can like when you are recovering the metadata index, as long as the number of servers do not exceed this predefined maximum server count, you're gonna guarantee that you can recover the index correctly. And So also we support these two different query modes, and also yeah. So these are the functionalities. And also for the local index structure, we have this local compound type-based indexing structure. And for this one to support especially for supporting the infix query, um, so we provide two different options. One is to enable the suffix tree mode, where the suffix query can be turned into exact queries, and then the infix query can be turned into prefix queries. So the idea is basically to permutate every suffix of every index key into the structure. The second option would be like inserting the inverted string for every index key. So in this case, suffix query is like treated as a prefix query. However, for infix query, you need a query broadcasting into scan all partitions and also the entire indexing tree locally. So, but with option one, you can have like better tree node utilization because tri-node utilization because you basically have a lot of redundancy or repetitive occurrence of characters when you actually permutate uh, the suffixes of the index key. And then for this one, because every inverted string is different from the original one, so you have lower tri-node utilization. So here is our experiment. And so for testing the capability for Dart to maintain a balanced node distribution, we picked three different data sets. That is a list of UID generated by a UID generator, and then a collection of words from a Oxford dictionary. And also we have this wiki data set that have all the keywords chunked from the wiki dataset. And then also also for this wiki dataset, we demonstrate like the number of queries, number of requests against different keywords. So you can see this long tail effect, like showing that different keywords have different popularities. And so the experiment that shows here we're measuring the capability for maintaining a balanced distribution with the metric of coefficient of variance. So here, as you can see, lower CV value means that we can reach to a more balanced distribution. So as you can see, for three data sets on different scale, Dart is maintaining a better distribution than the initial hashing. However, definitely, I mean, the full string hashing is 100% like better than any. But the thing is, with full string hashing, you need to do query broadcasting when it comes to affix-based keyword search. And also with this replication factor to be 3, here we can see that we may also maintain a very low request distribution, even lower than the full string hashing and the initial hashing. And after integrated with mediums, here is the query result that we compared with Meta that has the full string hashing capability, and also some of the database-powered solutions like that are employing the embedded database like SQLite. So here we're also comparing with mediums like with the suffix tree enabled and suffix tree disabled. So as you can see overall, as compared to Meta, we actually achieved 300 to all the way to 90K times performance improvements. And as compared to the SQLite-based approach, we achieved 370 to all the way to over 15,000 times performance boost. And also for the collective method search, we achieved up to 300 times performance boost as compared to Meta, and also we've achieved up to 180 times performance boost as compared to SQLite. So here are some of the key takeaways. So the key value format of the metadata in self-describing files like HDF5 really affect the design of the API and also the internal data structures that you choose. And also, because you need to support the queries against both keys and values, you need to make sure these two parts of the method attributes are considered in the query. And also, for the distributed and parallel method search, the key takeaway is that we need to make sure we minimize communication costs, and also we need to support both independent queries and also collective queries. And also we need to be able to deal with the, let's say, the scalability. And also, finally, the application of suffix tree actually the result is kind of surprising. It's different than what we thought initially. Actually, it brings better index performance, and also it is not burning too much overhead for the because of the final. So conclusion here. First, Dart enabled efficient Affix-based key search, and EDMs enabled efficient Affix-based key value method search in parallel data applications. So both works build a strong foundation for accurate Affix-based fuzzy method search in distributed environments. And here I would like to thank all of the co-authors that have been working on this project along the line. So that's all.
Thank you. Any quick question?
So you mentioned comparing against SQLite. Quickly, SQLite is like a single core application. How did you distribute it? Your tests. You said you did it across nodes. Just specifically, SQLite does not want on this like single core, single machine database.
Oh, you mean like the SQLite?
Yeah.
So the SQLite approach is like, so a lot of work actually employing the SQLite to serve as their backbone of the local indexing solution. So on the distributed setting, like each server maintains a process that talks to its own SQLite, let's say, library.
So you build something on top of.
Build something on top of that. Yeah. So it is actually there's a work we called Impress, and that is actually employing SQLite.
Another quick question is, how do you bring it back to HDF5? Want to bring the
Actually, considering HDF5, actually you, like I said before, you would consider you have multiple HDF5 files distributed on a parallel file system, right? And for that, you already naturally become like a distributed or let's say parallel application. And in that case, you need to consider like how do we minimize the communication cost when it comes to Affix-based keyword search. And so no matter if you have a, let's say, a middleware to support you for the access of against all of these HTML5 files or not, still you need to consider like even for all of these parallel processes, you need to consider okay how do we distribute the index properly to serve the efficient Affix-based keyword search or method search.
Right. I think we are about 7 minutes late. So let's start. Thank the speaker again.
Yeah.